the present electrical form. I'm also going to try to attempt to show the part that amateur radio played in both halves of this, the center being 1919. The first attempt to overcome distance by electrical means started in the 18th century with Leyden jars and long stretches of chain or wet string, Benjamin Franklin being one of these people. When Volta discovered the electrical pile and was capable of producing direct current, that opened the way for the experiments of Faraday and Henry in developing the electromagnetic telegraph. This development inspired the search for a wireless telegraph. With the advent of the Edison and Tesla power systems, the implement for wireless furthered. The declaration of Maxwell that electricity and light were analogous laid the groundwork, and Tesla's development of alternating and oscillating current devices naturally led to the electric wireless. Tesla was more interested in wireless power than wireless telegraph, that is, the wireless transmission of electricity. This led to far different results from those of Hertz and Marconi. Amateur radio played a part in the experimental development but was shut down in the massive global readjustment program following 1913. Free communications was not in the plan. Marconi stations such as KPH in Bolinas, California were seized, and RCA took over and eliminated the Marconi system, fashioned on Tesla's ideas. Following RCA's formation, amateur radio was restored and given the worthless frequencies above 1,500 kilocycles. Hams found that these frequencies allowed for very long distance but intermittent transmission by Hertzian means. RCA grabbed onto these frequencies and established electromagnetic radio. The Tesla-Marconi system was forever abandoned. The present amateur radio has abandoned all experimentation and has embraced the corporate instituted technologies of the New Babylon. Although amateur radio has the potential for the development of the Tesla non-electromagnetic radio system, the lure of the 2-meter yak-yak renders this development unlikely. In all likelihood, Tesla's important developments are lost forever. But let's see what's going on here. We track the history of, see if we get this to spin, history of wireless communications. It started with a person by the name of Matthew Loomis. What Loomis did is he chose 2 mountaintops 6 miles apart and flew 2 kites up into the atmosphere, roughly about 1,000 feet up. As you can see in the diagram, he hooked the telegraph key to one and a sensitive galvanometer to the other. And sure enough, when the key was hit on the other end, the galvanometer moved on the other end, and Morse code transmission was possible. You also notice that there's no battery, no Southern California Edison, no Pacific Gas and Electric. Edison tried to develop a form of wireless where trains with long wires stretched along them could communicate to the telegraph wires along the tracks, this being a magnetic system and very ineffective. Basically, these could be called single energy forms of transmission, and this one uses pure electrostatic, and this one uses pure magnetic. It's interesting to note that the electrostatic worked and the magnetic didn't. Then we move on to the double energy wireless, where the real progress was made. Hertz in 1880 found that he could transmit VHF and UHF signals by discharging a capacitor into a loop, a half-wave loop, and a half-wave loop at the other end would produce a spark. But this didn't work over a very great distance. Tesla found by taking 2 resonant coils and exciting one with alternating current would produce the appearance of electrical power at the other end. This worked at very far distances, and no RF amplifiers were required. It wouldn't light up a light bulb at the other end. As wireless progressed, Tesla established the system where he could transmit longitudinally through the Earth electrical power at a velocity of 291,000 miles per second. Also, he developed a beam tube.
What was that speed?
291,000 miles per second, pi over 2 times the velocity of light.
186,000 miles per second is C. I think you're exceeding C. Maybe kilometers?
No, it's pi over 2 times the velocity of light.
He is exceeding C. He'll go on and explain.
Okay.
There's a different set of dimensions.
All right.
Velocity of light simply is an expression of the ratio of energy to mass.
All right, which is a limit.
A limit to what?
As a constant.
It's a constant,
Yeah.
not a limit. In the beam, Tesla found that he could transmit direct current energy over incredible distances. And this energy not diverging out of the beam, much tighter and more compact than any laser ever built. In the longitudinal mode through the ground, there is really no losses, and the light bulb would light up at the other end. Marconi, in an attempt to circumvent the Tesla patents, changed the impedance of the system and used the flat top antenna, where you would get transverse electromagnetic propagations at 186,000 miles per second and longitudinal magnetic dielectric transmissions at 291,000 miles per second. For those that want to go back through history, Professor Wheatstone proclaimed that the velocity of electrostatic induction was pi/2 times the velocity of light. As those of you that know about electronics and electricity, I'm sure you all heard of the Wheatstone Bridge. Wheatstone was a very important researcher. As things progressed, we ended up with this. Thanks to Mr. Sarnoff and RCA, all of these things were eliminated, and we ended up with a system where transmission only propagated at 186,282 miles per second. And the losses in the system were total. This occurred in 1919, and by then Tesla vanished from the scene. Now, if we analyze these systems, we find that the longitudinal magnetodielectric system, that the electrostatic lines of force and the magnetic lines of force are directed in the same axis as the propagation of the electrical energy. In the Hertzian system, the magnetic lines of force and the electrostatic lines of force exist at right angles to the direction of electrical energy propagation, and this is what accounts for its incredible losses. In this system, we have little or no losses. In this system, we have an extremely high level of losses. In fact, by its very definition, it's resistance. It's called radiation resistance, a term familiar to many. And also, we have the waveforms that these devices produced. Now, we're familiar with the conventional alternating current. Okay, the alternating current has a real frequency in cycles per second. And it constantly cycles in a circular fashion back and forth. And then, of course, we know about the continuous current, or the direct current, which has no cycles per second. This would be called a scalar frequency. Scalar, by definition, is a quantity that does not vary in your system of variation, of either time or space or whatever variation you're talking about. Example would be like atmospheric pressure. Atmospheric pressure is the same everywhere in this room. And that's a scalar function. But if we take the function of the height of people in the room, obviously that's a spatial function. I can see all these waves moving around. So we have a scalar function, and then we have a regular function of variation in this dimension of space within this room. Now we have the waveforms that have become forgotten since the days of spark gap and wireless. One is the impulse wave, which is measured in decibels per second and has an exponential waveform. Where this waveform is expressed in sines and cosines, this waveform is expressed in hyperbolic sines and hyperbolic cosines, and never truly dampens out, but always approaches zero asymptotically. And then we have the oscillating current waveform, and this was the one utilized by Tesla. This waveform is expressed in cycle decibels per second. Now, in Tesla's time, he had a concept which he called individualization, where he would attune his resonant devices to respond not only to the cycles per second, but to the decibels per second, and produce a second order of tuning, where the waveforms would become much more individualized. Carrying this concept on further, if we take the resonant action of a simple LC circuit, it produces a sinusoidal function. But if we take the resonant action of a quarter wave transmission line, shorted at one end and open at the other, not only will it resonate at the fundamental frequency, but it will resonate at the third harmonic, fifth, and ninth, and ad infinitum all the way out. And it will produce this waveform. So we can see where we're in conventional tuning, we're using the sine wave. In the transmission line tuning, we end up with rectangular waves. Now, if we take the resonance of a coil instead of a linear transmission line, which is shorted at one end to ground and open at the other end, the harmonics are in phase, and we end up with impulses. Now, we find with the sine wave, the amplitude is the square root of 2 higher than what we would, rather than 1, it would be square root of 2 higher because of the peak to average ratio. With the rectangular wave, it would be 1. With the impulses, it's infinity. Now, what I attempted to show here is that in a measurable quantity of time, like on an oscilloscope, I used the black to show what we would see on the screen. Now, if we look at a square wave on the oscilloscope, we know that this transition is not visible because the amount of time occupied is infinitesimal. Now, with the impulse waveform, the pulses are of infinitesimal width. What I'm trying to show with the shading here is the integration that shows that the energy contained in the wave is the area underneath it. There is no area on this. The amplitudes are infinite. And these are the waveforms that Tesla were working with. And these waveforms would tend to punch through, where the continuous waveforms wouldn't make it. Now, I have a working model here. I can carry all this over and not get electrocuted. I don't think it's going to work, so I'm going to speak louder. I'm going to have to circumvent.
Take that mic. This is working real well. Not that one, the other one.
Yeah, I don't like being grounded by playing with 600
Yeah,
volts.
good idea.
Okay, I have a model of the Tesla transmission system. I'm going to go over this.
Take the big mic. That's what I'm saying. Take the one off the stand there if it'll come
Okay.
off. Just set it down anywhere. Don't worry about
It's
it.
called the one-handed electrician syndrome. Okay, what we have here is a number of demonstrations. This is a model of the Tesla transmission system, and the diagram up there shows basically what's happening. Here we have the conventional direct current power supply, and we have a small radio transmitter here, 400 kilocycles, the industrial, scientific, and medical band. Everything is conventional at this point. Here's our antenna, but it doesn't radiate any electromagnetic waves. Now, this antenna, as you can see by the RF ammeter, is transmitting roughly 10 milliamperes of displacement current into the earth. And this signal can be picked up at great distances through similar devices by transmitting through the ground. There's no electromagnetic radiation from this device at all. There's a very intense electrostatic field, however. This thing is hot. Now, the light bulb is the Tesla beam tube that transmits direct current through space. It's hard to demonstrate, but if I had a small electroscope, you would find that direct current is being transmitted from that filament because it's a hot cathode and transmitted radially out through space. And as I tune this device, if the filament is loose, you can actually see the filament expand and try to fill out in the space. There's an actual repulsive field around this device. Now, if we eliminate the light bulb, we eliminate the losses. And then we go to the simple ground transmission mode. And the current goes up to a little higher than before, still about 10 milliamps. This is a very crude, small device. Now, I've built these devices on the 40-meter band and powered them up to about 50 or 100 watts. And was successful with simply a coil hooked to a very low impedance ground of transmitting from the San Francisco Bay Area to Los Angeles with 599 plus. No antenna at all. No antenna. Very intense ground. 24 ground rods into a salt marsh, the San Andreas, the San Gregorio, and a third unnamed fault, all converging. And 500 feet of silicon bronze wire, all connected to a massive copper bus. Now, basically, if you view this device Let's start with the quarter wave vertical. Everybody's familiar with the quarter wave vertical. Okay, those of us that love 80 and 40 meters know that the quarter wave vertical is a real pain. So what do? We wind a coil. Right. So we wind the coil and then the antenna shrinks. But then we want to get rid of the antenna, so we wind more coil. But what does the coil do? The coil has capacitance. And then we keep on shrinking the antenna, and then the coil builds up more capacitance, until finally the coil becomes its own quarter wave resonant circuit. But its radiation resistance is 0. So our ground impedance must be 0. Because if we start off with an antenna current of 1 amp for a given amount of power into a quarter wave vertical, we're going to end up with a pure loading coil with no losses of a current of roughly 400 or 500 amps for the same amount of power. And that's going to put a heavy demand on the ground system. But if you can meet that, those poor people in their RVs that have that big coil and no antenna are going to have to turn their RF gain all the way down. And they're still going to be asking what you're doing, because they're going to hear every little squeak that your transmitter makes in between. Every bit of power supply hum, every bit of back wave. And they're going to keep on saying QRP. And it works. I've tested it. It does work. Now, I've developed various analogs of this. I have 2 analog computers here that simulate these type of waves. I'll move to my diagram here.
Just leave it down facing the speaker.
Eric, I don't even need that mic. Don't worry about it.
Okay, well, I got it now.
All right.
Okay, these are the various transmission paths we find on a resonant coil. We have the electrostatic, we have the magnetic, we have the magnetodielectric, and we have the electromagnetic. And all of these paths are circulating around the coil. It's a very complex transmission path, and analysis of it really boggles the mind, particularly for transient cases. And I had to develop a completely new system of algebra just to describe this stuff. And then I did manage to come up with practical algebraic formulas available for the ham radio operator experimenter that are published by a rather obscure organization up in Eureka called Borderland Sciences. And there's nomographs and tables to calculate your impedance and wavelength and all these things. It's completely engineerable. There's nothing mysterious about any of this at all. Okay, if we look at these constants here, K is what's called the elastance between the terms. Elastance is measured in per farads. Not farads, but per farads. Everything becomes inverted. Capacitance, of course, is measured in farads. This is the electrostatic impulse wave. This is the one that finds its way to the end first, the coil. And we have the magnetic wave, where L is the inductance in henries, M is the inductance in per henries, or what we're used to calling mutual inductance. Mutual inductance always has to be expressed as an inverse. It's always in per henries. Otherwise, the dimensionality does not work out, and the equations will lead to erroneous results. This really led to a lot of confusion in the early attempts of the GE laboratories to ascertain why these complex waveforms they were experiencing in their substation transformers were causing them to explode for no unexplainable reason. The standing waves would build up and appear in the center of the windings and puncture the insulation, but yet from terminal to terminal there was no voltage difference. The process was basically started off by Steinmetz, and then there were 2 other allied scientists, Bloom, and I forget the name of the other guy, Boyajian. Bloom was the first one to discover that the dimensionality of magnetic inductance should be, rather than L squared, L being length, should be 1 over L cubed. In other words, per centimeters cubed. But never went anywhere with it. And then Bewley, which was the one that really developed all the differential equations for describing this stuff, kind of forgot about mutual inductance in its proper dimensions. And even though quantified all of these things very admirably in his book called Traveling Waves on Transmission Systems, probably one of the best books on electric waves ever written. He still failed to understand the true nature of the longitudinal wave and the dimensionality of mutual inductance. Now, of course, in the double energy flows, when these things combine, we have the longitudinal wave, the wave of Tesla, and we have the transverse electromagnetic wave, the wave of Hertz. This is the wave we use today for transmission. This wave has become completely forgotten, unless it incidentally appears because you have too big of a loading coil. Oh, piece of paper there. Okay, I think that's it for the diagrams. Yep, that's the last sheet. Okay, that kind of wraps up what my talk is on this. I know it's a pretty shotgun approach and scatter, but I tried to run you through the whole arrangement here. I think any experimenter knows where to begin. You're going to end up with an SWR of infinity as your desire rather than 1. You're going to find out that the plate current will dip down real nice. Your tank circuit Q, irregardless of what the ham radio book says, should be at least 10 to 20,000. The way to accomplish this is with extremely heavy sheet copper windings and large quantities of vacuum capacitors in parallel. You'll end up with circulating currents of hundreds, if not thousands, of amps. The other approach is to use large series resonant circuits or resonant coils. You'll end up with voltages of anywhere between 50,000 volts to 1,000,000 volts. You will learn all about electrostatic gradients, punch through, flame outs, and all the pitfalls. It will be very difficult. And you will learn about ground impedance and the undesirability of inductance. A straight wire is no better inductance. There's no better way to establish an impedance than to have a nice long piece of number 8 gauge wire going from your rig to ground. You might as well put a resistor in the circuit. Everything has to be done with sheet copper. Any effective conductor of radio frequency current has to be 1/3 wide as it is long. It can't be any thinner. Ground impedance has to be at least 100th to 1,000th of an ohm. If you can deal with all these things, you can get rid of your antenna and you'll have no more complaints from your neighbor except for that did-it-ah-dah did-it coming out of their telephone. So I'm going to turn this over to Chris, and he's going to go through some ancillary. Oh, actually, I was going to give you one more demonstration here. I'm sorry. We have the two networks. We have the longitudinal and transverse networks.
Hold them up, Eric, and show it to them.
Well, it's kind of hard. But we have, as you see, the network MK and network LC, which is shown as 2 and 4 on there. These are laddered up in what are called an artificial transmission line, consisting of a long series of little capacitors and little coils. The transverse electromagnetic line here is 1,500 meters long, electrically. Now, if we hunt for its resonant frequency as a quarter wave transmission line, in other words, creating an impedance at one end and an admittance at the other end, or closed and open circuit. And we'll use the AC voltmeter here. You notice we only have to use one wire. That's the key to Tesla. He developed the true monopolar electricity. Okay, we'll hunt for a resonant frequency. Okay, we get a little kick there, a little higher than before. I'm not used to this oscillator, so I don't know what its calibration is. It seems a little different than the original. Things don't always work out on stage as you would like. Okay, it was supposed to be 53 kilocycles, so this is showing it about 60. Okay, that is network number 4 up there, where all of the inductances are in series and all of the capacitances are in parallel. This is the transverse electromagnetic wave. By the way, the characteristic impedance of these artificial lines is 2,000 ohms. If we terminated the end in 2,000 ohms, of course, we would have SWR of 1 and no resonance. But I chose to leave them open and close at the other end so we'd have the resonance and be able to see the resonant frequencies. Okay, now on the longitudinal, we hunt for the resonant frequency. And here it shows up as about 100 kc. So we can see that in the longitudinal, the wave is propagating much faster than it is in the transverse. This oscillator is off frequency. It worked out that this one was 52 and this one was 83. And it worked out to be approximately that the ratio of the longitudinal transmission to the transverse transmission was exactly as Tesla stated, pi/2. Now in the longitudinal, okay, we're used to dealing with transverse in a quantity which we call 1/c². Somebody just brought up that recently. The c being a basic ratio between the magnetic units and the electrostatic units of the electrical constants. And it gives us basically a propagation through space as a length over a certain period of time. In the longitudinal, we're not propagating through space. We're propagating through counter space. Counter space is a situation where rather than expressing the length in meters, we have to express it in per meters. A completely inverse form of propagation. As an example, if we take an electromagnetic inductance coil, we find the inductance is proportional to the length of the wire, approximately, and the area enclosed by it. It's the quantity of meters that expresses the inductance. If we take a capacitor, we find the closer we bring the plates together, and the more we fill in the area, we're dealing with a situation that's in per meters. The electrostatic, as a natural propagator of longitudinal waves, always goes towards closeness. The magnetism always acts as a distance. So here is our basic difference between longitudinal and transverse. In the transverse wave, we're attempting to overcome distance by forcing our way through it. In the longitudinal wave, the 2 points are already there. Why fight it? They're already one. And this was Tesla's fundamental discovery. This is the way that he was able to light up a light bulb at his receiver. No RF amplifiers. They didn't have any of that back then. There was no transistors, no tubes. There was no Radio Shack. There was no Newark catalog. There was no Henry. There was no ohm. There was nothing. All there was brass and wood. And that was it. There was nothing else. And this guy, Tesla, was capable of transmitting electrical power over incredible distances with just simple, practical materials. There was no silicon. There was no nothing to work with. They just started to develop vacuum tubes. His vacuum tubes were all just like the light bulb. They were all just one-terminal devices. And they would produce incredible quantities of light in the same fashion as the sun, completely unlike the incandescent light bulbs of today. And all of Tesla's devices never used energy. Just like in a tank circuit, it was always returned on the opposite half cycle. So that concludes my talk. I'm going to turn you over to Chris for a few more demonstrations. Hopefully it wasn't too far out or confusing for you. I'm sure it was a lot of material. But also, I think I gave you something to start experimenting with. So those of you that love 160 meters, go to work.
Coming second to Eric Dollard is very difficult, I assure you, because he can go on like this for probably about 5 hours, and we'll have you convinced at the end of the 5th hour. But I'd like to demonstrate something for you people that are not familiar with a longitudinal wave. I'm going to let Eric hold one in. Let's start off with the transverse wave. Now, as we hold this hose here,
Sideways flow.
you can see that it takes a finite time for this transverse wave to propagate from one end of this hose to the other. You can see there's a finite time. That finite time is the speed of light. And that is what we're considering our limit in the electromagnetic world in classical theory. Okay, now Eric and I are going to demonstrate the longitudinal wave, the one that travels infinitely faster than the speed of light and has no losses. Just jerk it like I said. As you can see, if you move one end, the other end moves instantaneously. There is no time delay as there is with the transverse wave. And it's very important to pay attention to that because that's the one we completely ignore. That is the pressure wave essentially through the ether, as it was. One way to describe it. But you should remember that little demonstration because we spend all our time looking at just one of two waves. The transverse wave is unfortunately the one with the losses. The longitudinal wave is the one with no losses that we don't even acknowledge exists. And that's also the one, I might add, how our minds transmit between each other. And that's the one that cells use to communicate with each other. It's the one that nerves use to communicate with each other. I have a more interesting chart. I'll use Eric's chart here. As you can see, if you were to stack these cells up here side by side of number 2 here, this is the transmission line with the capacitors in series and the coils in shunt. If you put another one here and another one and another one, what you find is you have 4 capacitors in a little cell-like structure. You have 4 capacitors, a coil shunt, 4 capacitors, a coil shunt, 4 capacitors, a coil shunt. It's my theory that the capacitors are the cell membrane of the cells next to each other, and the coil is probably DNA, would be my guess. And it is a guess, of course, but I've done I have a feeling that's how the nerve fibers work, and also probably how life itself develops energy from the ether and scalar fields. Of course, the concept of the ether was banned, when was it, Eric? 19...
Einstein.
Yeah, Einstein, yeah, basically. Einstein knew how it all worked, but he did not, was not allowed, shall we say, to divulge it. All right, I have a little lecture on 2 devices that I've found quite interesting, seeing as how nobody really understands how these things work. Everybody thinks they know how a transformer works. We're going to go over that one. And we're also going to go over this interesting device here, which I've been passing around for the last 15 minutes, ball bearing motor. Now, you can win a lot of bar bets with this one, and a lot of people would lose it, hands down. But all we do here is we take 2 ball bearings of any kind you want, connect them in this kind of fashion with an ammeter, connect to the outer race of each ball bearing, use a conductive shaft of some kind, makes no difference. I use brass, you can use steel, you can use anything you want, and get a 4 to 6 volt battery and just connect them to this thing, and you'd never think it would run, but it does. Eric and I need to get this started. You have to give it a...
0 starting torque.
You have to give it a spin. Stand out of the way of the thing. You have to give it a spin because its starting torque is very low. But its running torque is very high. Very interesting device. It'll run both directions, one polarity. So you can win a few bar bets with that one, let me tell you. And if anybody wants, I've tried it with about 5 different types of bearings. They all work just fine, and it doesn't seem to be fussy. You've got to get at least 10 to about 50 amps going through the bearings before it works properly. But Eric and I both thrashed this one around for quite a while, and I agree with Eric. It proves that we've got 2 vortexes operating here in the current somehow through the ball bearings, and the vortexes themselves are making the balls rotate. And that's another theory in itself, because the energy does vortex in and vortex out in the ether. All right, now we'll get into something a little more interesting. Does everybody know what a transformer is? They're on every power pole in every city, in every residential area, every industrial building. I work out of UCSB, and I deal with them every day. We've got probably about 400 of them out there, large ones. And they seldom cause any trouble, and but unfortunately, nobody really quite understands how they work. And you say, oh, I know how a transformer works. I learned it in electronics class and all that, and that's true, you did. But we're going to go through a little basic principles of electronics here and power generation, right, just for a second. If I take a magnet, bar magnet right here, and a piece of steel, and hold the steel up next to the bar magnet, what happens is, in classical thinking, the magnetic flux lines of the magnetic field are attracted to this piece of iron. The iron tries to close the field lines, and you get a concentration of field lines in the iron itself. Iron is like a sponge. It just kind of grabs all the flux lines up. And the other principle we learn in electronics is that if we take a bar magnet and cause it to move around a conductor with a meter on it, the moving magnetic lines of force cutting the wire field generates a current that you can read with a meter. And everybody has demonstrated that at some time or another, I'm sure. That's not anything. But the principle is the field lines cut the wires, and the wires somehow generate electricity. Interesting theory. On the primary winding of a transformer, this is a toroid. This is hopefully a perfect transformer. It has no core losses, and we'll just assume it has very good high permeability core. If you put an AC signal generator on this thing and your typical primary winding, the primary side we understand quite well, because when the current flows through the winding, the flux lines, it tries to make a bar magnet basically out of this piece of core right here, because you have turns around it and you have a piece of steel in it. So what happens is all the flux lines, just like this piece of iron up here, jump from the winding into the core itself, the magnetic core, and it forms a magnetic loop, actually a magnetic flux path around the transformer. And since it's AC in here, the magnetic field is changing both direction and magnitude with the alternating source. Is everybody following me so far? And nobody's disagreeing with anything? Okay, that's...
No way.
Are you?
No way.
You're not following. Well, you don't have to follow. That's all right.
The snake oil.
All right. Yeah, snake oil. You can explain this when I get through. Anyway, the problem exists in the secondary coil, which we all assume when the magnetic flux lines supposedly cross the winding of the secondary coil, it generates current, producing current in this arbitrary resistive load. The problem is that iron sucks up most all of the magnetic field. Like 98% or higher of the field will be within this red circle here, and within the iron, just like this thing, sucked up all the flux lines in here. And if there's any leakage flux, it's very small, and it's mostly around the primary coil, and it would be probably less than 1%. So almost all our magnetic field is within the red iron core, in this case. Now the problem exists is if the field is within the red iron core, no field line touches the secondary winding, because the winding is not within the iron. The winding is external to the iron. Now, if no field line touches the coil, the secondary winding, then no voltage or current will be generated in the secondary winding. Now, albeit physics has devised a bunch of cute little things that supposedly make this work. However, there is no flux line touches the secondary winding. So if no flux line touches the winding, it cannot induce a current, it cannot induce a voltage. So how does it work? And that is the question you might be able to answer.
You have to.
You can. Well, all right, fine. But there's no flux Now, the one answer you're probably going to give is if flux passes through a coil that generates a current, that's fine. But there's no flux line touches a wire here, which means there's no interaction between the core itself and the wire itself, which means what is interacting here. Truth of the matter is we have no idea how a transformer works, even though they're the most common thing around. There are many explanations, but I've never seen one that would, Eric has pointed this out to me, that really explains this properly. So, I have a few electrostatic experiments over there, and my next talk, my favorite subject is electrostatics, and this is kind of off my normal topics, but the next lecture I give will probably be on electrostatics, which is very interesting because we ignore them completely. We're all in tune with magnetic stuff and magnets and coils and wire, but nobody ever looks at the electrostatic force, which is where all the action is, and that's where the longitudinal wave interacts. Anyway, that's really all I have, and I'd like to thank you all for putting up with us tonight, and I wish you would invite Eric back sometime because he can go on, like I say, for about 5 hours here. Thank you very much.
Eric is going to answer questions. Yeah.
Yeah.
Okay.
The wheel going around, can you talk about
I will, yeah, I'll go. These are not really Tesla experiments. These are, Mr. Wimshurst invented this machine. This is what I call a dielectric induction machine. And I picked up that wording from Eric because the explanation of how this thing works is also not especially clear. The discs do not touch. The discs do not touch. There is 2 grounding electrodes on each side, and they're counter-rotating discs. Yet, as you can see, they generate quite nicely. The generation portion we really don't understand too well, although there's a lot of explanations for this thing, but none of which I'm satisfied with. Then the other side of it is an electrostatic motor, which I don't know if any of you all have seen one of these things, but I have a 3-foot diameter electrostatic machine. It works this thing a lot better than the little one here. But we just had so much stuff tonight, and we had an hour, so I decided we're just going to do this one. But these machines are interesting. They use no magnets. They have brushes. They seem to work best with glass epoxy, of all things. Seems to be the best thing that works. What you're doing is how to let Eric explain the thing actually, but the glass epoxy of the rotating dielectric is a thing where the field lines of the ether essentially are attaching to pieces of that dielectric, and when they counter rotate spin, one of them generates, one half the thing generates, the other half generates the opposite charge. It's I could get into a lengthy discussion of how the thing works, but it's not really. I don't think it's correct. So, but they do perform quite admirably. Everybody thinks
Mars or the sun. A lot of confusion resulted. It's found that the sun transmits no transverse electromagnetic energy whatsoever. The only thing you can see in space is reflected when the longitudinal fields strike a surface and turn into the scattering transverse electromagnetic waves. So what they did in favor for the astronauts is put in the special diffraction gratings on the windows so they could be convinced that they were really somewhere and not nowhere. And again, the practicality is for the 160 meter and 80 meter people, this is really the only way to go. And you'll find with these type of systems is they really don't use any energy. Your plate current would be practically nothing, for those of you that know what tubes are, or even know how radio works anymore. I know that's starting to get forgotten. I know there's only a few WAs and WBs around here, and there's one N6, probably can transmit 35, 40 words a minute. Any other? Yeah.
Is there any practical application of this actually in use in the world today?
I think it's all pretty much lost and gone. After 1919 and the closure and seizure of all of the Marconi stations, that was pretty much the end of it. And Tesla clammed up and became a total recluse, and all of his funding was cut off.
Not so.
Who continued his funding? We have somebody here that knows what Tesla did after 1919. I'm curious.
I'll bring the book to you. There's like court cases.
Oh, there was always court cases.
And this is quite lengthy explanations.
Tesla was involved in a court case where he was fighting for the survival of his Wardenclyffe Tower. And the, what would you say, the depositions or whatever, I don't know the legal terms of that court case, were recently published by a person by the name of Leland Anderson, which apparently is a competent electrical engineer. And when you read through this, you see Tesla saying over and over and over again that his radio was non-electromagnetic. Repeatedly, but it all fell on deaf ears. Once physicists grabbed a hold of electricity, all knowledge of it ceased. Electrons have nothing to do with the flow of electricity. Electrons are the rate at which electricity is destroyed. Electrons are the resistance. The waveform of electron flow is the same waveform produced when you slam on the brakes and you hear that horrible screeching sound. It's not a nice harmonic sine wave. It's a very bitter, horrible sound of energy dissipation and material flying everywhere. Electricity flows in the space between the wires. This has always been known by electrical engineers. For example, you short out a major electrical circuit, you will see the cables violently repel each other as the electromagnetic force tries to escape from the boundaries in which they're contained between the so-called bounding conductors. But most people are not electrical engineers and don't deal with the situation. I have to deal with it every day. I had a welder run away on me at work a couple of days ago, and every wire and every conduit tried like hell to escape the conduit. The noise was horrible. Everything repelled. Everything rattled. All the lights flashed, and all the computers failed. I love it. Any more questions? Yeah. Bruce De Palma did not invent the end machine. The end machine was invented by some people that lived in the bushes over the hill. And they actually produced, it's called a sunburst. I'm not that familiar, but I know Bruce De Palma. Bruce De Palma picked up on the idea and tried to duplicate it and produced a very wonderful constant current machine with horribly strong magnetic fields. It still did not produce the free energy.
They still have the overheating problem with it?
I don't know where it's gone now. He went overseas, and that was kind of the end of that. The problem is you get too high of a concentration of magnetic fields, and you're fighting a losing battle. Now what Chris did is Chris built an electrostatic equivalent of it, consisting of 1,000 picofarad variable capacitor that was spun by, I believe, a 10,000 RPM motor. RPM is the key. Same thing with Tesla. All of Tesla's true devices always spun at some horrible velocity. And this highly rotating, high-speed rotating variable capacitor, when hooked to a battery, would produce electricity from nowhere. I have a little device in my car where I operate my 24-volt military field radios off of 12 volts. Very crude device. It consists of a vibrator that charges two 12-volt capacitors in series and discharges, or charges them in parallel on 12 volts and discharges them in series on 24 volts. If the dwell angle on the contacts in the vibrator gets screwy, when you turn the switch off, the thing just sits there and keeps humming, powering the 327 pilot lamp for a period of about 2 minutes. But of course that's impossible, just like all Tesla's work. It's all impossible. It's like the transformer. That's why the lights should go out right now, but they're still humming away. Any more questions? Yeah.
The other speaker said something to the effect that Einstein was suppressed, quote unquote. My question is by whom?
Well, probably the same people that bulldozed my station in Bolinas and are now presently trying to close down KPH in Bolinas, which Marconi started in 1913. Same people that like to get rid of all those tubes and knobs on your radios. When I caught the fire department cutting my coax and said they didn't want any radios with knobs anymore. And the FBI said that the dope dealers were all upset that I was listening to their telephone calls, so the county came in with their SWAT team to get rid of my radios. It gets into a weird subject when you start to explore it. I'll tell you right now, the cellular telephone companies want to make the situation just like it is in the so-called United Kingdom. You better not get caught with a scanner in the UK, or you go to the brig. We will have none of your radios here, Mr. Dollard, and your experiments are banned in the town of Bolinas. We have a group to make sure. They even went so far as to cut down all the roadside telephones. So look up a group named Commonweal in Bolinas and talk to Hillary. They'll tell you who. It's up to you to experiment. I already lost a gallon of blood over it right out of the rear end. Any more questions? Yeah.
Where did you get your ideas for the design of these experiments up here? Is there some booklet you guys?
Well, it all goes back. You got to go to the library. I can give you some names: Steinmetz, Kennelly, Heaviside, Maxwell, Faraday, Bewley. Oh, let's see who else. Mathematician by the name of McFarland that worked out of Austin, Texas. Well, those are pretty much it. You work with those guys, and and do your basic studies. Learn the algebra, and learn your dimensionalities. It takes about 14, 15 years.
You're not on the internet, are you?
I'm on CW every day. 7037 in the morning and 7137 at night. The rest of it, as far as I'm concerned, is just the Babylonian telephone. Because that 2 meters isn't good for your face. I did experiments with the higher frequencies. They cause eye cataract, so I'd be careful about holding that stuff around your head. And these little silly phones that people carry around, I don't know. 15-minute exposure, and I found I was getting 100% mutation in radish seeds. Things are a little different than you would think right off. Any more questions? Well, I guess I scared everybody.
Eric, I'd really like to say thank you for a most informative evening. And I don't think anyone's been disappointed in the comment that was made that this will help you to think, I think is the word. We have a lot going on. We have one thing that we do, and we'd like to, we say thank you to our speakers. We have a little speaker's trophy just as a memento, just to say thank you very much. We really appreciate you guys being here.